Hey guys, welcome back to Bob and Mup Chem. In this video, we're going to be looking at bond enthalpy calculations. We're first going to define what average bond enthalpy values are, where we can find them in the data booklet, and then we're going to use them in some calculations, as well as look at some of the drawbacks of using them. But first, try this refresher question based on the video that we did on Hess's law. Pause the video and have a go. Looking at the overall equation and the first equation, we can see that that equation is the right way around because we want 1 mole of carbon, so we'll use that enthalpy change. However, the second equation, we're going to flip to get the negative of that, so we're going to use the positive 520, add those two values together and cancel the oxygens on either side, and we get the overall equation that we're looking for with an enthalpy change of 126, which is B. So what is average bond enthalpy? Well, the average bond enthalpy is the average energy required to break 1 mole of a chemical bond to produce 2 moles of gaseous atoms. An example of this, very simple one, would be Cl2 gas being broken into 2 moles of Cl atoms as gas. So you'll find all of these values in table 11 of the data booklet. All of the values are positive because they represent the amount of energy that is required to add to the bond to break the bond. So it always requires energy to break bonds, so these values are always positive. This can be very useful as we can make quick calculations to see what we'd expect in a reaction. However, because they are average values, that means they're values taken across many molecules. And so it doesn't take into account any variation in strength within the same compound or molecule. And it also doesn't take into account state changes. So this always assumes gaseous state. However, intermolecular forces can have an influence on these values. And so these values are only technically valid at SATP for gaseous molecules. And they also don't account for any energy changes that are due to being dissolved in water or any other solvent. That all comes together, meaning that energy changes that are calculated with these values are generally considered to be less accurate than those if they were calculated by a very good, and I mean good, experimental methodology. However, they're still really useful and is quite simple to do. So if we have our data table here on the right, we can always use the overall enthalpy change is equal to the sum of the bonds in all of the reactants, the bonds that are broken, minus the enthalpy of the bonds formed. Okay, so that's the energy put in to break bonds minus the energy given out to make them. For example, let's have a look at hydrogen plus Cl2 goes to 2HCl as a gas. So on the left-hand side, we have 1 H bond and 1 Cl-Cl bond. And on the right, we have 2 times HCl bond. So we can total up the values for our bonds broken, which is our reactants. So we look at our table, use it like an old bus timetable, and we look for hydrogen, crossing over with hydrogen, which is 436. We do the same with Cl and Cl, which is 242. And then that's going to give our total bonds broken. Then we do 2 multiplied by H and Cl where they cross over, which is 431 times 2. And then we just sum the total of this expression, which will give us the overall change for this reaction, which is equal to minus 185 kilojoules per mole. So as long as we're able to draw our Lewis structures of the molecules in question, we should have a pretty simple calculation to do. So let's have a look at another example, but this time using methane gas plus oxygen goes to CO2 plus H2O, classic combustion reaction. So the first thing we're going to want to do is we're going to want to draw out all of our bonds. That's going to make it easier for us to see which bonds we have and to do the calculation. So we've got CH4, which is obviously C bonded to 4 hydrogen single bond. O2 is a double bond, and remember we've got 2 moles of that, so bear that in mind. CO2, we've got carbon double bonded to 2 oxygens, and H2O, we've got oxygen bonded to 2 hydrogens, and we've got 2 moles of that in total. So we want to find out the sum of the bonds broken and the sum of the bonds formed. So we're going to look first for our carbon-hydrogen bond, which is 414. The oxygen-oxygen bond, double bond, is down at the bottom for the multiple bonds. So we do 498 multiplied by 2. That's our bonds broken. Then we're going to want to find our bonds formed. So we've got C double bond O. That's 804. And there's 2 of those in that molecule. So we multiply that by 2. And we add that to oxygen-hydrogen bond, which there is 2 of. That's 463, and we're going to multiply that by 4 because there's 2 whole molecules. That's our bonds formed. Then we just resolve that, which gives us minus 812 kilojoules per mole. So we can make a note here that the actual value of this, when it's determined experimentally, is minus 890. Now, we'd expect a certain discrepancy, remember, because in the calculation we've just done, we used average bond enthalpy calculations, and an experimental value doesn't use those. So we're always going to be a little bit off when we use these values. Okay, time for you to have a go. Data booklet might be helpful. I will put the values up, but they'll be quite small. First question, use the bond energy values to determine the enthalpy change for this reaction. Pause the video and have a go. Pop them up. Okay, using our equation and the values, we want to first draw it out. So we've got H bonded to H single bond and oxygen is double bonded. We only got 0.5 moles of that. Goes to H2O, which has 2 OH bonds. Then we just find the values for our HH bond, which is 436. Double bond oxygen is 498 multiplied by 0.5. That is our bonds broken. And our bonds formed is 2 times the oxygen hydrogen, which is 463. Then we do bonds broken, take bonds formed, which gives us minus 241 kilojoules per mole. Okay, so have a go with this reaction for the Haber process. Pause the video. Pop 'em up! So again, always good when we first get started to draw our Lewis structures of all of the molecules. So we have triple bond N, then we have hydrogen again times 3, and we have ammonia, which has 3 NH bonds and 2 moles of that. So we're going to total up our bonds broken. So we look at our multiple bonds. They give us a value of N triple bond as 945 and the hydrogen bond as 436 multiplied by 3. And then for our ammonia, we've got NH bond. Now there's 3 per molecule and we've got 2 moles. So we're going to do 391 times 6. And then we're just going to subtract those bonds broken from the bonds formed, which is minus 1093 kilojoules per mole. One more question for good luck then. Another combustion one, but a little bit more complex. Pause the video and have a go. Pop them up. So still following the exact same way as before, drawing out our Lewis structure so we don't miss out any bonds. So we've got C2H6, got 6 of those CH bonds, OO again, but we've got 3.5 times the number of moles of that. We've got 2 times CO2, which means we're going to have 4 total C double bond O, and we've got 3 times H2O, which means we're going to have 6 OH bonds. So first of all, looking at our bonds broken, we've got 346 plus 6 times 414, which is for the C2H6, plus 3.5 times 498. So that's all of our bonds broken. Now for our bonds formed, we're going to have 4 times C double bond O, which is 804, plus 4 times OH, which is 463. So the total of in the green gives us our bonds formed. So of course, once again, we do bonds broken minus bonds formed, which equals minus 4637 kilojoules per mole. So we are going to do a practical on this, and we'll also use this practical for our mock IA. And there's some questions in the practical workbook, as well as some calculation questions to do too. Thanks again for joining me, guys. Don't forget to like, subscribe, hit the bell icon, and as always, practice makes slightly better.